All right, I'm on page 348, where it begins talking about plate tectonics. What is plate tectonics? Continental drift was not widely accepted in the scientific community, but over time, more evidence was collected and scientific thought about moving continents changed. Scientists eventually modified continental drift into a theory called plate tectonics. Plate tectonics states that Earth's surface is made up of giant moving slabs called tectonic plates. Tectonic plates divide Earth's outer layer, which is called the lithosphere. Under the lithosphere is the asthenosphere, where differences in temperature and pressure cause material to slowly move. This motion causes the tectonic plates above to move also. For a hypothesis like continental drift to be modified into a theory, a great deal of evidence must be gathered. In science, a theory is a system of ideas that explains many related observations about the natural world. The theory of plate tectonics explains how moving plates shape land features. It also explains how plate motion relates to Earth processes such as volcanic eruptions. Okay, so let's go back through this one paragraph that's sort of introducing the idea of plate tectonics. First of all, it says that continental drift was not widely accepted in the scientific community. Okay, part of the problem with plate tectonics not being widely accepted was that Alfred Wegener, the one that proposed continental drift, he couldn't explain how the continents had moved. He had pieces of evidence that said they did move, that there were coastlines that fit together, that there were fossils on two different continents that were the same fossil, all of these other pieces of evidence that we talked about in the first screencast. But part of the problem with his continental drift was that he couldn't explain how or why that had happened. So I want to take a moment and have you guys write that little snippet down so that we understand that that was part of the reason why Wegener's ideas were a little bit slow to catch on. And I'm going to go back to page 347 and write it down. Okay? So Wegener couldn't explain how the continents have moved. Okay, so he said that they had moved, but he couldn't explain how they had done it. All right, so let's go back to page 348. Let's talk about plate tectonics. Okay, so continental drift was not widely accepted in the scientific community at the time because Wegener couldn't explain why they moved or how they did it. But scientists eventually modified continental drift into a more comprehensive theory known as plate tectonic theory. Plate tectonics states that the Earth's surface is made of giant moving slabs called tectonic plates. And here's a map of the Earth, or a globe, and it's sort of broken in sort of an expanded view of many of the plates that you find on the surface of the Earth. So we live over here in Texas, and we're on this big piece. It looks like a little piece of broken eggshell. This is the North American plate. This is the Caribbean plate. This is the South American plate. This is the Nazca plate. I think that one's the Cocos plate. This out here is the Pacific plate. Over here, this is the African plate. This is the Eurasian plate. But they all fit together like giant pieces of a puzzle, okay? And they are made out of lithosphere, which is the solid rocky upper crust and upper mantle, okay? They float along on sort of a semi-liquid rubbery layer in the upper mantle called the asthenosphere. Okay? In the asthenosphere, you get pressure and temperature differences which cause material to move. Okay, material moves in the asthenosphere because of convection currents. Okay? So convection currents move material in the mantle, and remember that the asthenosphere is the upper part, one of the upper parts of the mantle. Okay, what is a convection current? If you don't remember what a convection current is, it's the concept that warm fluid is less dense and therefore it rises, and cooler fluid is more dense and so it sinks. So you have this circulation of fluid. It can be convection currents in the atmosphere, which we'll look at when we study weather. It can be convection currents in the ocean, where warm water rises and cooler water sinks, or it can be convection currents that we find in the mantle where warmer, less dense molten rock rises and a little bit cooler molten rock sinks. Okay, so it sets up these convection currents, these areas of circulation. Okay, then it says for a hypothesis like continental drift to be modified into a theory, we need a great deal of evidence. And a theory is a system of ideas that explains many related observations. The theory of plate tectonics explains how moving plates shape land features. It also explains how plate motion relates to Earth processes such as volcanic eruptions. Okay, so then we go to the question, how is the theory of plate tectonics related to the hypothesis of continental drift? Well, plate tectonics is a theory that explains how the continents drifted. So it adds to continental drift, and it's an improvement on Wegener's theory of continental drift. So it's basically an improved version. Then we ask the question, what evidence supports plate tectonics? Plate tectonics explains that the continents are not actually drifting. Instead, they are parts of giant moving plates. All of the evidence that supports continental drift also supports plate tectonics. Research about the sea floor began in the mid-1900s and provided key evidence for the theory of plate tectonics. Part of this evidence came from mapping the sea floor and discovering Earth processes such as sea floor spreading. Evidence also came from discovering magnetic patterns in sea floor rock and from mapping locations of earthquakes and volcanoes. So now we're going to talk about those pieces of evidence that support plate tectonic theory. Okay? So we need to recognize that all the evidence that supported continental drift also supports plate tectonics. Evidence comes from mapping the sea floor. Evidence also comes from discovering magnetic patterns in the sea floor and from mapping locations of volcanoes and earthquakes. All right, so piece of evidence number one is sea floor spreading. So this is piece of evidence number one. Studies of the seafloor revealed underwater mountain belts called mid-ocean ridges. Okay, so we have like these underwater mountain chains, and they run along the middle of the oceans. Like this is the mid-Atlantic ridge. It's this underwater system of mountain ranges. And this is where the seafloor is spreading. These other areas under different oceans are the same sort of thing. It's where the sea floor is moving apart and spreading. Okay? So the process by which new seafloor forms is called seafloor spreading. As new seafloor rock forms, it pushes the existing rock in opposite directions away from the ridge. As the seafloor spreads away from the mid-ocean ridge, the far edges of the seafloor are destroyed. Or it could be just the far end of whatever tectonic plate we're talking about. Okay, so the edges are pushed. All right, so they didn't really explain what edges. Edges are pushed into deep ocean trenches through subduction. Subduction, sub means under. So subduction is the process by which one tectonic plate is pulled or pushed beneath another tectonic plate. Okay. For instance, let me give you an example. Here is the west coast of South America. This whole thing here, this whole area, okay, This whole entire area is the South American plate, this whole thing. So it goes from the mid-Atlantic ridge all the way over here to the west coast of South America. This whole thing is the South American plate. Okay, well, new ocean floor is being created right here, and it's moving, the whole entire plate is moving this way to the west. Well, that means it's bumping against or pushing against this plate right here, and this is the Nazca plate. And the Nazca plate is actually being forced and pushed under this edge of the South American plate, and that's called subduction. And there's lots of places around the world where subduction is occurring. Okay, so piece of evidence number 2 is properties of the seafloor, and I'm going to stop my screencast here and we'll pick up with properties of the seafloor on screencast number 3.